Okay, so welcome to G03 lab number 2. So we're going to continue our work before where we're looking at array of Illumina nanopore data. We mapped the reads with Lab2, which performs better arguably for longer reads. And we did the same also with BWA MEM2, which arguably works better for short reads. And we did initial processing with SAMP tools, and we're going to continue that and also progress on to accumulating some summary stats for the different read libraries using SAMP tools, and also implement that further with QualiMap, which also does similar work using a range of different approaches. So we're at this point where we're okay. So a convenient tool we can use is called SAMP tools flagstat. This is a range of parameters, but mainly all we need is simply the orm-dup file. So we start with our nanopore data map with Minimap. We can run that. And you can see there we have summary information on that. So we have 22,840 reads in total, and nearly all of these have been mapped properly. If we look then at the BWA version, it's the same library. So we actually see that we have slightly more reads there initially in total, and then, well, slightly more reads in total that mapped, and 344 that are partial maps. If we look then at our nanopore read library, which is would be the recent one, that's this one here. So it's called a flagstat is the command. Just send it our BAM file, orm-dup BAM file. We find that we have far more reads, 590,000 and 294,000 and half of which have properly mapped. And we can also compare this to the BWA mapping for the same one. And there we see that we have, in fact, it's nearly the same, mapped properly as well in this instance. So very, very comparable values there. But that information kind of gives us some summary information, especially for read pair information that could be quite much more complex to look at. Another convenient tool we can use, let's use that previous one, the Illumina library with BWA, MEM2. We can use this to go coverage, and that gives us the summary coverage for this library. So we look here, we've got the reference genome, start, end, the number of reads, the covered basis, which is nearly all. The coverage is 99.6. Mean depth is, sorry, the covered basis is 99.6%. The mean depth is 2,500, which is very hard, very high. The mean base quality is 33, and the mean mapping quality is 60. So you can see those metrics are all very good. And the mapping with Minimap should be very, very similar. It just takes a minute to go to the number of reads. We see slightly fewer reads, slightly fewer covered bases, slight differences here, but it's really, really minute. But if we then compare this to the BWA MEM2 mapping for the nanopore library, we will find some differences. So you see here we got the number of reads is 23,000. Covered basis is similar, actually even more this time. We've got a mean depth of 660, and then a mean base quality of 23 with a mapping quality of 30. So the coverage is very, very good, and the coverage is good, but the quality is not as good as Illumina data, but the structural resolution is going to be higher. And for the other one with Minimap, we see that we have yeah, very, very similar metrics there all the way through. So that means we can kind of tabulate and assess which is best for our task. The next step is to use this tool called QualiMap2. So you can download this. If you look at the worksheet, there's a command called wget, and that gets files from the internet. So it expects a URL in there. And you're going to use this one from a website called Bitbucket. And this website has QualiMap downloadable as a zip file. So you can do that there. And that will access that file from that website. And it's just exchanging keys. And then you'll have this file locally stored here. Let's show it. So you see it there. So you just want to unzip it. And that will unzip it. And then you go into the directory, change directory into there, and you'll actually find that there's no real executables to be installed. It runs straight away. So that's the executable there in front of us. So if we run that, we need a dot and a forward slash in front to know that we're executing it inside this directory. Okay, that's the Java implementation. So what we want then is, let's try to run this. So what we want to do is to log on with X11 forwarding on. So I'm just going to pause and do that. Okay, so when you open Column it may give an error, but that's just an OR package detail. So you just see a panel like this. So what you want to do is go to File, New Analysis, and we're looking at BAMQC. We're not looking at RNA-seq data here today, but we could do QC with this approach, this tool on that. We're not looking multi-BAM QC yet, but we'll look at that later. So we just try BAM QC on its own. We'll click on that, and that will give us a file menu when we simply want to examine. Let's see, examine advanced options. Not really useful for us. We just want basic analysis, and we have to go to the right folder of where our data is. So what we want to do is open files ending in ormdup. So they're recently examined. I open the window a bit. So let's look at the Illumina BWA one first. So we'll open that and hit Start Analysis. And you can see that's starting to be analyzed there now. So you can see what's nice about this interface is that it gives you a visual summary straight away, which can be quite handy if you're trying to kind of get a handle on a complex data set. So you can see there we had many reads, which we looked at before. We look at the mean read length is 192 bases. There's 96.8% of reads are duplicate, most of which are clipped as you would expect. The GC is what we would expect. The coverage is very high all the way through. Mapping quality is high. We see that there's mismatches across the different reads, so that's going to correspond to the number of reads. That's roughly half a mismatch per read. And we see that there's relatively fewer insertions and deletions. And then we see there's certain homopolymers. If you look at the coverage across the genome, you can see that it's quite variable. Definitely very variable, probably amplicon sequenced. If we look at the coverage histogram, you can see it varies quite a bit. The fraction of the genome covered is high. The duplication rate is high in certain instances. The ratios of A, C, G, and T is kind of what we would expect across the read lengths, except maybe the 5' end is not great. GC content is more or less what you would expect. Homopolymers, again, is lower for C compared to nanopore. And then the mapping quality across the reference is very good. 60 is the max, as I mentioned. And see that that's all looking good. So we can decide to do a new analysis. And maybe we'll look at the Illumina and Minimap data. So note again, I need to select all files and just sorting by time to know which one I want to get. So Illumina, this one, I think I will start the analysis with that. And you should see this panel appearing before you. Again, you can see it's very similar to what we had before. We can look at it to see if there's any difference. The coverage is very high again. Mapping quality is high. We see that there's general error rate is low. There's similar insertions, but more. Is there more deletions? Are there more deletions here? And then the coverage is very good again, although very variable due to amplification. You can see that the mapping quality across reference is very good. So let's now look at the nanopore data. So we can expect that will be somewhat contrasting. So if you look at the nanopore data, I can find it. So let's look at the minimap one first of all. So we see here now we have far fewer reads. Duplication rate is lower, still high, but lower. Mean coverage is still high, albeit lower than the previous. General error rate is 4.3%. There's far more insertions than deletions, so nanopore data is maybe less informative about true insertions and deletions. And most reads have at least one insertion. If you look at the coverage, you can see it's amplicon sequenced. It's pretty clear, but it's contiguous, which is great for resolving the true structure. If you look at the coverage is high. Duplication rate is lower. The nucleotide end is quite consistent up to about 1200 bases, and then the 5' end also is poor again, as we'd expect. GC content indicates some sort of slight shift there, maybe something else is in there. Homopolymers is what we comparable to Illumina. Mapping quality is still very high in terms of the uniqueness of the reads. And then if we finally take our new analysis and do BAMQC on then the BWA mapped reads for the same nanopore library, we can see that it's slightly more reads, but it's very, very similar metrics all the way through. Higher levels of mismatches in insertions and deletions, perhaps. We can compare and contrast them. We can see the summary information. Yeah, 24,000 insertions, 198,000 deletions, 112,000 insertions, 170,000 deletions. That's kind of comparable. Finally, if we wish, we can export the report as a HTML. So let's call it just out1 for simplicity. We can also export this as PDF. So polymap report 1. And then what else can we do? We can compute the counts for files that are of interest. And then we can also run multi-sample BAMQC and add our samples in here if you want to. So you could add a particular sample from a library. Just for example. So that's the end of quality map for this part. So what we can do now is switch to our Unix window and look at how we can do it using the command line. Okay, so let's look at the results that we had before. Let's look at google.chrome, and we want to look at the 2 reports that we had. That should be in the current folder. So we've out1, so we go into out1, and we can see there that we have the quality map report in there. So we can use the google.chrome application to open that up. And we can view that here. So we're looking at that report now, and this really contains the same information, just in a HTML or format. So this is kind of the input basics in terms of the details. And if you scroll further down, then we find the information we had before, just in a different format. And this is for the final sample we were looking at there, but we could do it for all the reports, and it's the identical information we talked about already. So let's switch back, and if we looked at there's other information inside this folder as well. So there's things like the images for each of the items of interest. There's things like the actual raw data, if that was of interest. And then we also could have the look at the PDF report as well, if you wish to. So QualityMap also has a command line version as well. which could be more convenient for some of you. So there you have to tell which function it's doing. So it's quality map BAMQC. And what you need to do then is go back one folder because I'm in this current folder. So think about it, I'm in this folder. So I need to go back to my, let's say, nanopore sample, the VWA mapped one. That's my input. I need to specify my output file and my output format as per the instructions. So I'm going to call it by its name and BWMM because that's the version. And the output format is HTML. Okay. Let's double check I got the commands correct. So it would help if I get the command right. So I have to put quality map BAMQC and then indicate the flag for the BAM file here. So I've done that. I've got the BAM file. I've got the output file name that I want, which is long because of multiple files, and the output format is HTML. So I'll run that. I see that it's iterating through creating those results as a HTML for that file. So this is more convenient if you want to write a script to run this on multiple files. So let's see where that is. So there you can see so let's try that here. So we have our file there created sorted stats. So we can see into that. And we see the same output format that we had before. We have the images there, the raw data, and then also a file called genome results, which contains the kind of summary information of the command, and then the kind of basic details of all the alignment, like the text information in our report there. So that could be handy for our, if we want to automate some of these processes. And then we also have the HTML file generated here. So we've repeated that for each of our different files that would tell us more about what has been found here. So the next step would be then to tabulate this for our different libraries and compare and contrast them depending on the features. What we can see here is that for the Illumina data and the nanopore data, that there's no consistent difference really between these mapping tools here. That essentially means that whichever one we assessed, it wouldn't really make a difference. But it's important to compare these metrics, especially if we're dealing with bigger genomes. So might find there's bigger differences there. And certainly you'd want to include both Illumina and nanopore data for a lot of those assemblies where we saw that there's features that are limited by one data source only. So that kind of concludes our demonstration video on this lab. We've kind of looked at this ideas about how to map different types of read libraries to reference genomes and assess the output that we get from them to kind of get a better sense of the picture of what we're looking at. We looked at how we can do that with shorter and long read data and how we can link them together with genome assembly. So the next step would be to de novo assemble those, map the reads to those, and look at mutations that could be present. And that's something that we'll do in the next course, G04, which is on mutation detection. And it's important that you understand this course well, so that because in that course we'll have mapped short and read, long reads, libraries to reference genomes to call SNPs, and this all help us understand our results as we go along, and is also very, very applicable to transcriptome data. So please come along to the labs that will be coming ahead in a few weeks' time.